Time?
We're just on schedule, so it's a bit.
Okay,
Got
thank
6
you.
minutes.
Okay, thank you.
All right. So up next we have Akin here from University of Surrey.
Yeah.
Just to give his work on learning human reconstruction.
Mm-hmm.
All right. So let's give it up for Akin.
Hello everyone, I'm Akin. I'm coming from University of Surrey. I'm working with Erwin Mustafa, Evren Imre and Edrin Hilton. Actually, in the scope of my research, I'm focusing on the volumetric reconstruction, volumetric human reconstruction, 3D human reconstruction. Normally, in the available systems in the market, there is the studio environment, a control environment, and lots of camera, like up to 100 camera. But in the scope of our research, we try to do it with better accuracy, with less camera, and for uncontrolled environment. So here is a general 3D reconstruction, multi-view 3D reconstruction capture system. Dynamic. There's a dynamic scene. There are camera inputs, as you can see here, and this is the reconstructed 3D output. When we look at the multi-view 3D scene reconstruction literature, there are two approaches. The first one is model-based one. In the model-based one, there is a parametric model, like simple model. I'm sure lots of people are knowing it in this room, and we try to estimate the parameters, but those models are limited, actually giving you limited 3D resolution. No hair details, no cloth details, no wrinkles, only the human body shape, like naked body shape. But on the other hand, in the model-free methods, you can estimate all the details like clothes, hair. Most of our work will be related on model-free methods. But when we look at the pipeline of those methods, they first start with estimating the dense stereo correspondences in between stereo cameras. And then after getting the view-dependent depth maps, we fuse them in order to get the final 3D reconstruction. But the most important part here is estimating dense stereo correspondences part. The methods which are available in the literature, they are dealing this step because we are dealing with wide baseline. I'm going to show it in the later slide, what is the wide baseline, what is the difference in the narrow and wide baseline. But they handle those stages with some initial reconstruction. For example, these three methods using multi-view camera capture system in order to get first visual hull. And for example, this one is using some sparse reconstruction as initial model, and then handle the estimating dense stereo correspondence part. But in my research, the first thing I focused on is what is the problem in this dense stereo correspondences? Why we need some initial reconstruction to handle wide baseline? When I look at them, there are some observations I want to share with you. They are, first of all, susceptible to ambiguities, textureless or repetition textures, and negatively affected by lighting conditions. And most important thing, they are sensitive to wide baseline changes. I mean, in order to identify what is baseline, this is the stereo camera, and this is the baseline in between two cameras. We can represent it with any distance, but I prefer to represent it with the angle here, theta. Here is a good visualization here. If we apply the state-of-the-art dense stereo correspondence method actually without using any initial reconstruction in 40 and in 60 degree baseline, here are the results. We cannot use it as a final product. Those reconstruction quality is not enough for us to actually go in the second stage, I mean depth fusion. So we focus on. When we look at the literature in a general, I want to skip this part quickly. We already covered this part. We also saw that there is a gap in the literature. First, in the deep neural network-based methods, no one is previously discovered the DNN, actually deep neural network-based wide baseline stereo. And also guidance is very important in the stereo because the other methods are using visual hull or sparse reconstruction as a guidance, but no one has ever actually discovered the semantic segmentation because it's very perfectly well in the wild. So we propose a method. Can we learn dense wide baseline stereo matching for people? But in order to do that, we need 3D human data and we need learning framework, and we need to put them together. First of all, I want to talk about the 3D human data. As many of you know that in the 3D domain, there is a lacking of data, I mean large data set, in order to learn something. So we propose, can we learn in a synthetic world, and can we learn as realistic as possible? So we came up with an idea. First of all, we are generating a simple model with random parameters, and we are adding realistic texture on them. Once we get the 3D human with the shape, we are adding previously captured motion sequences on top of them, and we are generating some realistic human motion with the realistic texture, and then we're placing stereo cameras in various baselines, and then we're rendering them as realistic as possible by using Blender, first of all, and then we are extracting the positive and negative patch in order to train our stereo match network. Here's our dataset. We call it synthetic people stereo patch dataset, and we are calling it S2P2. Here are a couple of stereo images, as you can see. It is the URL. You can actually reach the dataset, but the framework and the dataset in the latest version will be available in 2 weeks, just for notice. And if you want to use that, we will be happy. But in more details, this is this is as realistic as possible. These are human models with random background, but we are only using the patches on the human body. We can extract positive and negative patches. We can add some data augmentation, and we can get some reference positive and reference negative patch in order to train our network. There are some highlights I want to talk about. The first one is this is the first large-scale stereo dataset for people. There are some numbers, like 300 simple models we are generating. We are generating these models with the around 300 human textures and 100 motion sequences. Just for this paper, we generate around 12 million stereo patches to train our network. But with this framework, stereo images for various camera baseline can be generated, and realistic textures and human motion can be added, more realistic textures and human motion. But this framework allows not only the generation of data for multi-view reconstruction, but also for multi-view human tracking, multi-view human body pose estimation, and you can add more items into this list. After handling the 3D human data, we propose a solution. How can we learn stereo match? And we came up with this method. This is the overview of our method. First of all, we extract patches in different sizes, and we are putting them into our CNN network. And in the CNN network, we have feature extraction and the feature matching part here. And then after the pooling layer, we are using winner takes all. But since we are dealing with the wide baseline, we are using some semantic segmentation mask limitation for stereo search space. This is applicable for in general scenes. For example, in the studio capturing, since it is a control environment, we can segment the foreground and background easily by using some alpha mapping K. But in the wild, since we are developing our method for in the wild application, we prefer to use some off-the-shelf human semantic segmentation method to limit the search space for epipolar search. So here are some results. When we compare the closest competitor, actually in terms of RMSE values for 20 degree and 40 degree, around 40 degree baseline, we can see that our method is outperforming the closest competitor by 25%. Here are some depth results, but in order to see them in more details, I want to get your attention on point clouds in 2 different views for both datasets. When we look at them, even in the 22 degree, we can follow the surface reconstruction better than with our competitors. But if we increase the baseline up to 40 degree, now our method actually shows itself, and we can get more accurate surface reconstruction, even if we are not doing heavily post-processing. For example, our competitor MCCNN, they are doing semi-global matching and bilinear filtering for post-processing. Instead, we are only doing some light drive disparity consistent check. That's it. Here are some results in the time domain. I also want to show that these are some results with clutter background. Even with the clutter background, we can get the images without using any initial reconstruction by only using our stereo matching method, trained on synthetic data, not fine-tuned on real data. This is an important part. And here are some conclusion remarks. Learning from synthetic dataset shows promising results in our case, in our domain. And if it is not possible to handle real capturing, especially human, and 3D human is one of this area, synthetic data fills the gap to some extent. And considering the feature of AI will be unsupervised, but we still need data, so it's a good way to generate data. And synthetic data generation for human-centric task save time and save money, because you need advanced camera capturing system to get some annotated data. As my last remark, the next stage in synthetic data generation should be more realistic. I mean, more realistic in terms of rendering, not rasterization, but raycasting. And in terms of human cloth, in terms of details, hair details, cloth details. So I just want to share one of our recent dataset generation. It's completely different from the previous one. but we can actually get more realistic rendering with hair and cloth details on top of it. Right now we are working on it. We are about to publish a paper by using this. After this publication, we're going to release it. But we believe in that we can fill the gap in between synthetic data and the real data by using this as realistic as possible synthetic data generation. So thank you for listening to me. If you have any feedback and a question, I would like to actually hear.
Any questions?